The moon is no longer just a distant light in our night sky. It's rapidly becoming humanity's next great frontier. What was once the stuff of science fiction is now the focus of intense global interest, with nations and private companies racing to lay claim to its untapped potential. And for good reason. Beneath its dusty surface lies a treasure trove of resources: helium-3, rare earth metals, and other valuable materials worth trillions of dollars. These aren't just scientific curiosities, they're the building blocks for future energy solutions and advanced technologies that could transform life here on Earth and beyond. But here's the real game changer. Mining these resources isn't just about pickaxes and drills. It's about cutting-edge robotics that can operate in the harshest environment humans have ever attempted to conquer. In this video, we'll dive into how the moon is shaping up to be the foundation for humanity's next chapter, exploring the mind-blowing technologies and groundbreaking ideas that are turning lunar mining from a dream into an imminent reality. The moon's rise as humanity's next mining frontier is not just driven by ambition, it's a necessity. Our planet is running low on critical resources that power modern life. Rare earth elements, essential for everything from smartphones to renewable energy technologies, are becoming harder and more expensive to extract here on Earth. Then there's helium-3, an isotope so scarce on our planet it's almost mythical. But on the moon, it's abundant, embedded in the lunar soil from billions of years of solar wind exposure. Helium-3 holds the potential to revolutionize energy production as a fuel for nuclear fusion, offering a cleaner, virtually limitless power source without the radioactive waste that plagues current nuclear fission processes. Imagine a future where energy is no longer a bottleneck for progress, all made possible by lunar mining. Yet, the moon's appeal isn't just limited to what's buried beneath its regolith. It's about the strategic role this celestial body can play in humanity's broader cosmic ambitions. Experts are already envisioning an off-Earth economy, where resources mined on the moon fuel not only industries back on Earth, but also enable deeper exploration of our solar system. Lunar ice, for instance, can be split into hydrogen and oxygen, forming rocket fuel that could transform the moon into a refueling station for spacecraft headed to Mars or beyond. The moon could serve as a springboard, our first step in becoming a truly multi-planetary species. This ambitious vision didn't just spring out of nowhere. It builds on decades of human curiosity and exploration. The Apollo missions of the 1960s and 70s were groundbreaking, not just for putting humans on the moon, but for showing us what was possible. They gave us our first samples of lunar material and sparked interest in the moon's resource potential. Fast forward to today, and the stakes are much higher. With nations like the United States, China, and India ramping up lunar missions and private companies like SpaceX and Blue Origin joining the race, the quest to mine the moon is no longer a distant dream, it's a fierce competition. But with opportunity comes challenges. The environment on the moon is unimaginably harsh, with temperatures swinging from blistering heat to freezing cold, radiation levels that would be deadly to humans, and a lack of atmosphere that complicates everything from machinery operation to long-term habitation. Traditional mining techniques simply won't cut it out there. That's why the key to unlocking the moon's potential lies in advanced robotics technologies designed to perform with precision and resilience in an environment completely inhospitable to life. And these aren't just robots as we know them. They're autonomous systems, smart machines, and innovations that redefine engineering as we know it. Lunar bases will be the beating heart of any moon mining operation, serving not just as logistical hubs, but also as safe havens for the humans and machines driving these missions forward. Picture them as self-sustaining outposts, complete with habitats where astronauts can live and work, all while managing the complex operations required to unearth the Moon's hidden riches. These bases will be equipped with life support systems to provide breathable air, clean water, and temperature control in an environment that's anything but welcoming. After all, the Moon's lack of atmosphere means there's no protection from cosmic radiation or the extreme temperature swings, which can range from scorching heat during the lunar day to bone-chilling cold at night. But that's just the start. Energy generation will play a critical role in keeping these bases functional and operations sustainable. Solar power is the most viable option, especially in regions near the Moon's poles, where some areas experience nearly constant sunlight. These peaks of eternal light, as they're called, could become prime locations for harvesting solar energy to power everything from mining equipment to life support systems. Storing this energy for the long lunar nights lasting about 2 weeks is another challenge scientists are working to solve, with innovations like advanced batteries and fuel cells under development. Then there's the question of infrastructure. Unlike Earth, the Moon doesn't have the luxury of pre-existing roads, pipelines, or supply chains. Lunar bases will need to support mining equipment, transport systems, and storage facilities, all while dealing with the abrasive lunar dust, also known as regolith, that clings to surfaces and can damage machinery over time. Building and maintaining this infrastructure in such a hostile environment requires a level of precision and adaptability that traditional construction methods simply can't deliver. This is where robotics come in. Robots are already being designed to perform tasks like assembling habitats, laying down roads, and even constructing protective domes using the Moon's own resources. For instance, by melting the regolith into a solid material, robotic systems could create structures that shield astronauts and equipment from radiation and micrometeorites. This concept, often called in-situ resource utilization, is a game-changer, allowing lunar bases to reduce their reliance on costly supplies from Earth. But the challenges don't stop at construction. Once operational, these bases will need constant maintenance to survive the harsh lunar environment. The lack of atmosphere means no weather to erode surfaces, but it also means no protection from meteor impacts or radiation-related damage. Autonomous robots equipped with artificial intelligence could be deployed to inspect and repair systems, ensuring that critical operations run smoothly without putting human lives at risk. What's exciting is that we're beginning to see this vision take shape thanks to initiatives like NASA's Artemis program. This international effort, which includes partnerships with other space agencies and private companies, aims to land humans on the Moon and establish a sustainable presence. Meanwhile, private ventures like iSpace and Robotic are developing innovative technologies to support lunar infrastructure and mining. These collaborations are paving the way for a new era of exploration, one where the Moon could serve as both a home base for deeper space missions and a steady source of resources for Earth. And this is just the beginning. The success of these lunar bases will hinge on the ability to integrate advanced robotics into every aspect of the operation. From autonomous rovers prospecting for resources to smart machines managing daily maintenance, these technologies will be the backbone of lunar mining. In the next section, we'll explore some of the most groundbreaking robotic innovations and how they're set to transform what we thought was possible on the Moon. When it comes to unlocking the Moon's vast potential, advanced robotics isn't just a tool, it's the ultimate game changer. In an environment as extreme as the lunar surface, where humans face life-threatening conditions at every turn, these robotic systems are stepping in to do the heavy lifting, literally and figuratively. These aren't your average industrial robots either. The machines being developed for lunar operations represent the cutting edge of technology, blending autonomy, artificial intelligence, and specialized engineering to handle challenges unique to the Moon's low gravity and unforgiving terrain. Take autonomous rovers, for example. These vehicles are akin to the Swiss Army knives of lunar exploration. Designed to traverse the Moon's rugged landscape, they can map the terrain, search for resource-rich areas, and even collect samples for analysis. Thanks to advancements in artificial intelligence, these rovers can make real-time decisions, avoiding obstacles and adapting their routes without waiting for commands from Earth, a critical capability given the time delay in communication between Earth and the Moon. One standout example is NAS, a volatiles investigating polar exploration rover, or VIPER, which is set to explore the lunar South Pole. Equipped with specialized drills and sensors, VIPER will hunt for water ice and other resources that could support future lunar bases. Then we have AI-driven excavation machines designed to do the hard work of mining under conditions that would be impossible for humans. These robots are equipped with intelligent systems that allow them to identify and extract valuable materials like helium-3 and rare earth elements with pinpoint precision. Their ability to operate continuously without the need for rest or life support makes lunar mining not only safer but also economically viable on a scale that simply wouldn't be possible otherwise. For instance, the European Space Agency has been working on robotic systems like the Regolith Advanced Surface Systems Operations Robot, or RASA. This machine uses lightweight, counter-rotating drums to excavate lunar soil efficiently while maintaining stability in the Moon's low-gravity environment. Robotic arms are another key innovation, and they're designed with flexibility and dexterity to perform a wide range of tasks. Whether it's assembling infrastructure, repairing equipment, or handling delicate samples, these arms are engineered to function seamlessly in the Moon's reduced gravity, which is about 1/6 of Earth. Companies like Boston Dynamics are pushing the boundaries of robotics with innovations that could easily be adapted for space applications. Imagine their highly mobile, adaptive spot robots outfitted with specialized arms, assembling habitats or managing inventory in a lunar outpost. What makes these robotic systems truly remarkable is their ability to reduce the risks to human lives. By taking on dangerous or physically demanding tasks, robots minimize the need for human astronauts to expose themselves to the harsh lunar environment. Beyond just safety, this also opens the door to scaling up mining operations in ways that are cost-effective. Instead of relying on large human crews and continuous resupply missions from Earth, autonomous robots can operate independently for extended periods, significantly lowering the logistical and financial barriers. The economic feasibility of large-scale lunar mining is further bolstered by collaboration between private companies and government agencies. NASA, for instance, has partnered with firms like Robotic and Intuitive Machines to develop lunar landers and rovers tailored for mining and exploration. On the private side, companies like ispace in Japan are innovating with compact, versatile robotic platforms designed for prospecting and resource extraction. These advancements are not just theoretical, they're happening now, with robotic prototypes already being tested in environments that simulate lunar conditions. And this is only the beginning. In the next phase of development, we're looking at robotic systems that can interact with each other as part of a coordinated network, a swarm of robots, if you will, each performing specialized tasks in harmony. This would make it possible to create fully autonomous mining operations, from excavation and processing to transportation and storage, all without the need for a single human on site. As we move forward, one thing is clear: robotics will be the backbone of our efforts to transform the Moon into a hub for resources and exploration. But what makes these machines uniquely suited for mining tasks? Let's dive deeper into the specific systems and technologies that are setting the stage for this new era of innovation. Mining the Moon is no small feat. The surface may look barren at first glance, but with the right technology, it holds immense potential for resources that could revolutionize industries on Earth and fuel deeper space exploration. At the heart of this operation are robots machines specifically designed to tackle the unique challenges of prospecting, excavation, and material processing in an environment unlike any other. Before any mining begins, the first step is prospecting, locating the areas most rich in valuable resources like water ice, helium-3, and rare earth metals. Unlike traditional prospecting on Earth, where geologists can physically examine the terrain, lunar prospecting is entirely reliant on robots, autonomous systems equipped with advanced sensors, spectrometers, and ground-penetrating radar scout and map the lunar surface, identifying areas where these resources are most likely to be concentrated. These robots use AI-powered mapping algorithms to analyze the data they collect, creating detailed resource maps that guide the next phase of the operation. For instance, NASA Viper rover is specifically designed to explore the Moon's south pole, where permanently shadowed regions may harbor vast deposits of water ice. By drilling into these icy patches, Viper will provide critical insights into the composition and distribution of this resource, which is essential for sustaining life on the Moon and producing rocket fuel for future missions. Once the resources are found, the next challenge is excavation. This isn't as simple as shoveling dirt. Lunar regolith or moon dust poses significant hurdles. It's incredibly fine, almost like powdered glass, and clings to everything it touches. This makes traditional excavation equipment prone to wear and tear, especially in the Moon's low gravity, where soil behaves differently than it does on Earth. Here's where specialized robots like NASA RASA or Regolith Advanced Surface Systems Operations Robot come into play. RASA is designed to dig efficiently in low-gravity conditions using counter-rotating drums that scoop up regolith while keeping the robot stable. Its lightweight, modular design makes it easy to deploy, and its ability to operate autonomously allows it to work continuously without constant human oversight. These features make RASA a perfect example of how robots are tailored to overcome the Moon's unique challenges. Material processing is the final piece of the puzzle, and it's just as critical. Once resources like regolith or water ice are extracted, they need to be processed into usable forms. For instance, water ice can be split into hydrogen for rocket fuel and oxygen for life support. To accomplish this, robotic systems equipped with specialized tools will be deployed to refine these raw materials on site, minimizing the need to transport unprocessed material back to Earth. The European Space Agency's Prospect drill exemplifies this approach. It's designed to extract volatile substances like water ice while heating samples to analyze their composition. This not only ensures precise resource extraction, but also provides valuable data for future missions. What's fascinating about these robotic systems is their ability to collaborate with one another as part of an integrated network. Prospecting robots can share data with excavation machines, which in turn communicate with processing units to streamline the entire operation. This level of autonomy allows for sustained mining efforts without constant guidance from Earth, where communication delays can make real-time control impractical. But even with all this automation, the success of lunar mining isn't about robots replacing humans, it's about working together. Human engineers and scientists play a critical role in designing, programming, and maintaining these machines, while astronauts on the Moon will oversee operations and make high-stakes decisions that robots can't handle. The collaboration between human ingenuity and robotic precision is what will make lunar mining not only possible but sustainable for the long term. And as impressive as these machines are, they're just one part of the bigger picture. The resources they extract and process will fuel humanity's ambitions far beyond the Moon. driving innovation here on Earth and paving the way for interplanetary exploration. In the next section, we'll take a closer look at how these mined resources are set to transform industries, enabling breakthroughs in energy, manufacturing, and space travel. The future of lunar mining doesn't just depend on building bigger, better machines. It's also about making smarter, more versatile ones. Enter modular robotics and swarm technology, two groundbreaking approaches reshaping how we think about mining operations on the moon. These systems are all about adaptability and efficiency, crucial traits for tackling the unpredictable and often harsh conditions of the lunar surface. Let's start with modular robotics. Think of these as high-tech Lego sets, robots built from smaller, interchangeable units that can combine, separate, or reconfigure themselves depending on the task at hand. Imagine a mining operation where the same robotic system could transform from a prospecting rover into a drilling machine or a material transporter, simply by rearranging its components. This flexibility eliminates the need to send multiple specialized machines from Earth, reducing launch costs and ensuring that the mining operation can adapt to unexpected challenges. If a module breaks down, it can be swapped out without jeopardizing the entire operation, a massive advantage in an environment where repairs and replacements are not easily accessible. One example of this concept is the research into reconfigurable robotic systems being developed for space applications. Picture a set of small robotic components that can link together to form larger, more complex machines as needed. They could operate as individual units to survey the terrain, then combine into a single structure to assemble infrastructure or excavate lunar soil. This kind of design also makes it easier to scale operations up or down, depending on resource demands or mission goals, without needing an entirely new fleet of robots. Now, let's talk about swarm technology, a concept that might just sound futuristic but is rapidly becoming a reality. Instead of relying on a few large robots to perform mining tasks, swarm technology employs a group of smaller, coordinated robots that work together like an army of ants. Each robot in the swarm may have limited individual capabilities, but collectively they can achieve complex goals. This approach is ideal for the moon's surface, where the terrain is both unpredictable and vast. Swarms can distribute themselves across a wide area, covering more ground in less time, and they can dynamically reorganize to focus on high-priority tasks when rich resource deposits are discovered. Swarm bots, as they're often called, bring exceptional redundancy and resilience to mining operations. If one robot in the swarm fails, the others can continue working, minimizing downtime and ensuring the mission stays on track. Additionally, their smaller size and reduced weight make them easier and cheaper to transport from Earth. Once deployed, their decentralized nature allows them to adapt to environmental changes in real time. For example, if a lunar dust storm, or what's known as a particle transportation event, disrupts a mining area, swarm robots can shift their activities to clearer regions without the need for direct human intervention. Real-world projects are already exploring the potential of swarm robotics for space. The European Space Agency and other organizations are testing prototypes that demonstrate how small groups of robots can work collaboratively to build structures or perform synchronized tasks like excavation and sampling. These experiments highlight how such systems could be deployed on the moon to not only mine resources, but also support broader goals like constructing lunar bases or maintaining infrastructure. But here's where it gets even more exciting: the role of artificial intelligence and machine learning in these systems. When you have hundreds or even thousands of robots working together, managing and optimizing their behavior becomes an enormously complex problem. This is where AI comes in, allowing these swarms to learn from their environment, improve their efficiency over time, and make independent decisions based on their observations. For example, machine learning algorithms could enable swarms to identify the most resource-rich areas by analyzing geological patterns or optimize their movements to save energy, ensuring the operation is as sustainable as possible. AI also enhances modular robotics by making it easier for systems to determine how best to reconfigure themselves for new tasks. Imagine a situation where a robotic system detects a shift in mission priorities, perhaps a sudden need to focus on extracting water ice instead of rare earth metals. With AI, the system could autonomously decide to shift modules into a configuration better suited to the task, ensuring that the mining operation continues seamlessly without delays for human intervention. Together, modular robotics and swarm technology represent a paradigm shift in how we approach lunar mining. They bring unprecedented flexibility, efficiency, and resilience to operations in an environment where adaptability is key to survival. And as AI and machine learning continue to evolve, these systems will only grow more sophisticated, unlocking new possibilities not just for mining the moon, but for exploring and utilizing other celestial bodies in the future. Next, we'll take a closer look at how these robotic innovations tie into broader advancements in artificial intelligence, driving the next generation of space exploration and resource management. Artificial intelligence and machine learning are the true brains behind the brawn of lunar robotics, enabling machines to operate with remarkable autonomy and adaptiveness in one of the harshest environments imaginable. On Earth, humans and robots often work hand in hand, with engineers tweaking systems, redirecting machinery, and managing operations in real time. But on the Moon, this dynamic shifts dramatically. Communication delays, which can take several seconds one way, make traditional remote control methods impractical. Robots need to think for themselves, navigating unexpected challenges and making decisions instantly, often without waiting for instructions from Earth. That's where AI and machine learning step in, transforming lunar robots into problem-solving systems that can evolve and improve with each task. One of the most vital applications of artificial intelligence in lunar mining is optimizing excavation patterns. Robots equipped with AI can analyze the composition of the lunar soil in real time and adjust their digging strategies to target only the most resource-rich areas. For example, if a mining robot detects a high concentration of helium-III or rare earth metals in a particular patch of regolith, machine learning algorithms can guide the robot to prioritize those zones, reducing wasted effort and maximizing efficiency. This level of precision not only saves time but also conserves energy, a critical factor when every watt counts on the Moon. Imagine a scenario where a swarm of autonomous robots works simultaneously, each equipped with AI to ensure they're not duplicating efforts or depleting resources faster than they can be processed. The result is an operation that's not just effective but also sustainable. AI also plays a crucial role in predictive maintenance, another game-changing feature for lunar robotics. On the Moon, where repairs are far more complicated than simply calling in a technician, anticipating issues before they become critical is essential. Machine learning systems can monitor sensors embedded in robotic components, tracking performance metrics like vibrations, temperature, or wear and tear. By analyzing this data, AI can predict when a part is likely to fail and schedule maintenance tasks before breakdowns halt operations. This approach reduces downtime and ensures that mining systems remain functional even in the Moon's extreme conditions. Consider how similar predictive maintenance systems are already revolutionizing industries on Earth, from aviation to manufacturing. Technologies like these are being adapted for space exploration, ensuring that lunar operations run as smoothly as possible. Navigation, too, is an area where AI shines. The moon's terrain is riddled with craters, boulders, and steep slopes, presenting significant obstacles for rovers and mining equipment. Traditional path planning methods would struggle to keep up with the dynamic challenges of such an unpredictable environment. AI-driven navigation systems, on the other hand, use vision-based technologies and depth sensors to map the surroundings and make instant decisions about the safest and most efficient paths forward. Machine learning algorithms enable these systems to learn from experience, improving their ability to avoid hazards with every mission they undertake. A prime example of this is the European Space Agency's development of AI-powered rovers, which are designed to autonomously assess risk factors while traveling across challenging extraterrestrial landscapes, effectively charting courses that humans couldn't manage from Earth in real time. But perhaps the most impressive aspect of AI and machine learning is how they enable robots to adapt to the unexpected. Lunar missions are filled with uncertainties. A mining robot might encounter a patch of unusually compacted regolith or realize that its planned route is blocked by a previously unmapped crater. Instead of waiting for humans to troubleshoot the situation, AI allows these robots to improvise. Using logic-based decision-making models and experience gathered from previous tasks, they can decide how to proceed, whether that means adjusting their digging methods or rerouting themselves around an obstacle. It's as though these machines are not just tools but collaborators capable of thinking critically about their tasks. The autonomy provided by AI is essential for the sustainability and long-term planning of lunar operations. A self-sufficient system of intelligent robots can operate continuously without the need for constant oversight, allowing mining operations to scale up efficiently. This autonomy is particularly important when considering the ultimate goal: to establish fully functioning lunar bases that support not only mining activities but also human life and additional space exploration missions. By minimizing human intervention, reducing waste, and maximizing efficiency, AI ensures that lunar mining isn't just a short-term endeavor but a foundational step toward building humanity's presence in space. As we look ahead, the role of AI will only grow, shaping how we approach sustainability in lunar operations. In the next part, we'll explore how these advancements connect with the broader vision of developing eco-friendly, long-term systems for living and working on the moon, systems built not just to endure, but to thrive in harmony with the challenges of this new frontier. As humanity ventures toward mining the moon, sustainability and responsible resource management emerge as key priorities. While the moon may seem like an infinite expanse of resources, its delicate environment presents challenges that demand careful planning and ethical consideration. Without proper safeguards, lunar mining could risk depleting critical resources, disrupting potential scientific discoveries, or even altering lunar conditions in ways we don't yet fully understand. This is where technology, particularly robotics and advanced automation, steps in, not only to maximize efficiency but also to ensure that exploration and extraction activities align with principles of environmental responsibility and long-term viability. One of the most promising strategies for sustainable lunar mining is in-situ resource utilization, or ISRU. At its core, ISRU involves using the moon's natural resources, such as regolith, water ice, and even sunlight, to support operations without relying heavily on materials brought from Earth. This approach dramatically reduces the cost and environmental footprint of lunar exploration by minimizing the need for constant resupply missions. For instance, lunar regolith can be used to build infrastructure, from landing pads and roadways to protective domes that shield against radiation and micrometeorite impact. By leveraging the resources already present on the moon, ISRU helps create a self-sustaining system that supports both mining operations and potential lunar habitats. Water ice, another critical resource found in the moon's permanently shadowed craters, has enormous potential for ISRO. When split into hydrogen and oxygen, water ice can serve as rocket fuel essential for future missions to Mars and beyond. It can also provide drinking water and breathable oxygen for astronauts stationed on lunar bases. However, harvesting and processing water ice must be handled with care to avoid excessive depletion and to preserve future exploration opportunities. Robotic systems equipped with precision tools and AI are uniquely suited for this task. They can survey, mine, and process ice deposits efficiently, ensuring minimal waste while maximizing output. The role of robotics in ISRO extends far beyond extraction. Robots are central to the entire life cycle of resource use on the Moon, from gathering raw material to refining it into usable forms and even recycling waste. Automated systems can transform lunar regolith into construction materials through processes like sintering, which involves heating the soil until it fuses into a solid structure. Meanwhile, smart waste management technologies can reclaim and reuse resources from mining operations, reducing the overall environmental impact. This closed-loop approach reinforces sustainability by optimizing resource use and minimizing unnecessary extraction. But sustainability is not just about efficiency, it's about balance. The Moon is more than a treasure trove of resources, it's a site of immense scientific and cultural significance. Its untouched geology holds clues to the history of our solar system, while its quiet, undisturbed environment is perfect for astronomical research and deep space observation. Overmining or reckless exploitation could threaten these opportunities, raising important ethical questions. For example, how do we prevent resource-rich areas from becoming overly industrialized, blocking future generations from making their own discoveries? And who decides how these resources are shared and managed? These are not just technical challenges, they are moral and geopolitical ones that demand international cooperation and foresight. Fortunately, technology offers solutions that align with these ethical concerns. Robotics and automation allow mining activities to be targeted with unprecedented precision, avoiding unnecessary disturbances to the lunar surface. Autonomous systems can monitor environmental changes in real time, ensuring that operations remain within acceptable thresholds of impact. For instance, AI-driven models could help simulate the long-term effects of mining certain areas, guiding decision-making to prioritize preservation alongside exploration. These technologies empower us to extract value from the Moon while maintaining its integrity as a scientific and cultural landmark. As we look ahead, integrating sustainability into lunar mining isn't just a question of ethics, it's a matter of survival. Without efficient resource management and minimal environmental impact, the long-term viability of lunar operations could be at risk. The Moon's resources represent an incredible opportunity, but with that opportunity comes responsibility. To ensure a future where space exploration and humanity's cosmic ambitions thrive, we must embrace technologies and strategies that prioritize balance between exploration, exploitation, and preservation. As we consider these technological and ethical challenges, there's another layer to this discussion: the geopolitical and economic implications of lunar mining. Who controls these resources and how will they shape the global balance of power? In the next section, we'll explore how nations and corporations are positioning themselves in this new space race and what it means for the future of humanity's relationship with the Moon. The advancements in lunar mining robotics are not just igniting technological progress, they're sparking a modern space race, a competition that could redefine global power dynamics and reshape the economic landscape here on Earth. Unlike the Cold War-era rivalry that saw the United States and the Soviet Union battle for supremacy in space, today's race is more complex, involving not only nations but also private corporations with their sights set on the Moon's untapped resources. This interplay between governments and businesses is setting the stage for an unprecedented surge in innovation, economic growth, and potentially geopolitical tension. At the heart of this modern space race lies the dual promise of economic opportunity and strategic advantage. The Moon's resources, such as rare earth metals, helium-3, and water ice, represent incredible gains for nations or companies that can successfully extract them. Rare earth metals are critical for the production of advanced electronics and renewable energy technologies, industries that are already fueling the 21st century economy. Meanwhile, helium-3 holds the potential to revolutionize clean energy through nuclear fusion, a breakthrough that could make energy shortages a thing of the past. Water ice, as mentioned earlier, could serve as the essential ingredient for propellants, effectively transforming the Moon into a refueling station for deeper space exploration. The first entities to establish control over these resources will not only reap massive economic rewards, but could also gain a significant technological and strategic edge. However, this growing interest in exploiting lunar resources is forcing us to confront a complex legal and ethical question: who owns the Moon? The primary legal framework governing space activities, the Outer Space Treaty of 1967, dictates that no nation can claim sovereignty over celestial bodies. It also emphasizes the peaceful use of space for the benefit of all humankind. But as private companies like SpaceX and Blue Origin, alongside nations like China and India, push forward with ambitious lunar mining plans, the treaty faces challenges it was never designed to address. For instance, while it bans national ownership of the Moon, it remains unclear how it applies to resource extraction. Can a company or country claim ownership of the materials they mine? If so, how do we prevent monopolization, where a single entity gains disproportionate control over lunar resources and the industries they fuel? Efforts are underway to modernize space governance in light of these developments. The Artemis Accords, led by NASA, aim to create a shared framework for the exploration and use of lunar resources. These agreements promote transparency, peaceful collaboration, and the idea of zones of non-interference, which are intended to prevent conflicts over mining sites. However, not all nations have signed on, with some viewing the accords as favoring the interests of certain countries over others. This divergence underscores the risk of fragmented approaches to space governance, where competing interests lead to potential disputes or even conflict in space. The economic implications of lunar mining are just as profound. Successfully tapping into the Moon's resources could birth entirely new industries, from space-based manufacturing and construction to off-world resource processing and transportation. Imagine a future where jobs are no longer confined to Earth but extend to lunar outposts, where engineers, scientists, and technicians manage operations across millions of miles. The ripple effects would extend far beyond the space sector, bolstering industries such as robotics, artificial intelligence, and clean energy. This could lead to an economic boom similar to the Internet revolution, with new markets and opportunities redefining global economies. But alongside these opportunities come risks. Resource monopolization could widen the gap between nations and corporations with access to space and those without, exacerbating global inequalities. Countries or companies that dominate lunar mining could wield massive economic and political influence, controlling the supply of critical materials essential for modern technologies. This raises the specter of dependency, where spacefaring nations become the gatekeepers of resources vital to global industries, shifting the balance of economic power. Beyond economics, the geopolitical stakes are enormous. Space is becoming a new theater for strategic posturing, with nations viewing lunar operations as not just a commercial venture but a matter of national security. The Moon's south pole, with its abundance of water ice and near-continuous sunlight, has already emerged as a hotspot for future activity. Nations are racing to secure footholds with missions planned to lay claim, not in ownership but in presence over key regions. This competition could foster collaboration as countries recognize the benefits of pooling resources and expertise, but it could just as easily lead to tensions if perceived inequalities or encroachments arise. Ultimately, the race to mine the moon is about more than just resources. It's about shaping humanity's future. Will we create a cooperative framework that ensures space exploration benefits everyone, or will we repeat the mistakes of Earth's past by allowing competition and inequality to dominate? As we look to the heavens and imagine the possibilities, it's clear that the choices we make now will define humanity's relationship with the moon for generations to come. The moon, once a symbol of wonder and mystery, now stands as a gateway to a new era of exploration, innovation, and responsibility. What we do next will echo far beyond our time, setting the course for how humanity evolves as a truly interplanetary species. The idea of building lunar bases and using advanced robotics for mining on the moon represents one of humanity's most ambitious and transformative endeavors. It's a vision that combines cutting-edge technology, bold exploration, and the timeless human drive to push past boundaries and discover what lies beyond. The possibilities are as vast as the lunar landscape itself. With robotics leading the charge, we have the potential to unlock resources that could redefine industries, power sustainable energy solutions, and even serve as a springboard for further exploration into deep space. The moon, once viewed only as a distant celestial body, could become a cornerstone of our future, a place where science, technology, and dreams converge. Robotics, without a doubt, will be the linchpin of this extraordinary effort. These machines, equipped with artificial intelligence and designed to operate in the harshest conditions, will do far more than mine for resources. They will build infrastructure, maintain systems, and pave the way for human settlers to live and thrive in an environment that was never meant to support life. By working tirelessly, efficiently, and autonomously, these robotic systems will allow us to extend our reach far beyond what was once thought possible. They will show us that even in a setting as alien as the moon's surface, human ingenuity knows no limits. However, this vision is not without its challenges. The moon is a place of extremes with no margin for error. Success will require innovation on an unprecedented scale, developing technologies that can withstand the moon's harsh environment, creating sustainable systems to support long-term operations, and navigating the complex ethical and geopolitical questions that come with tapping into extraterrestrial resources. How do we ensure that lunar mining benefits all of humanity, not just a select few? How do we balance economic opportunity with the responsibility to preserve the moon's unique environment? These are questions we must answer as we prepare to take our first steps toward building a spacefaring civilization. Yet, while the challenges are daunting, the rewards are equally profound. The resources we extract from the moon could power not just industries on Earth, but entire missions to other celestial bodies. The technologies we develop to solve the challenges of lunar mining will spur innovations here at home, from advancements in renewable energy to breakthroughs in robotics and artificial intelligence. And perhaps most importantly, the moon could become humanity's stepping stone to the stars, a place where we learn how to live, work, and thrive beyond the confines of our home planet. This journey is a testament to the limitless potential of human ingenuity. It's a story of exploration, resilience, and the courage to dream big. While we can't predict exactly how the next few decades will unfold, one thing is certain: the moon represents both a challenge and an opportunity like no other. It's a chance to redefine what's possible and to inspire future generations to continue reaching for the unknown. So, what do you think? Could the moon truly become the gateway to humanity's future among the stars? What challenges or breakthroughs do you see on the horizon? Let us know your thoughts in the comments. We'd love to hear your perspective on this incredible topic. And if you're as fascinated by the future as we are, don't forget to hit that subscribe button and join us for more deep dives into the technologies shaping tomorrow. Together, we'll continue exploring the frontiers of human innovation and asking the big questions that will define our future. Thanks for watching, and we'll see you next time as we journey further into the possibilities of what's yet to come.